So again, we're kind of switching gears. We've gone from problems that involve generation, that are 1D and 2D, to now problems that are going to start incorporating time as a variable. That's what we mean by transient, is something that's changing in time. So the first way of tackling these types of problems is to think of the simplest possible example of a problem that depends on time. And that's something called a lumped capacitance problem. So if you've had any heat transfer before, you probably recognize this. But we're going to do this by going through an example. The example we have is some metal sphere. Maybe it's like lead shot or something like that. Pretty dense, relatively high conductivity. And the idea is that you have this sphere, and it's sitting in some environment. And the temperature of that environment is changing with time. And that is described by this equation here. So this is just our specified ambient temperature in degrees Kelvin as a function of time, so there's a relatively quick, less than a second change. And what we're trying to do is figure out what is the temperature of this body as a function of time. So yeah, again, we have this T infinity as a function of time is this unknown constants, or known constants, A 0 through 3 is a polynomial. Okay, so how do we go about solving this type of problem? So there's a couple things. Let's get to place in the notes here. So there's a couple conceptual things that we're going to need to do first. So to solve this problem, I mentioned the idea of lumped capacitance. We need to first convince ourselves that we can model this entire thing as a single temperature. What is the simplest possible function would be something where we say the temperature of this body depends only on time. Right? We throw out all the spatial dependence of temperature and say, give me some moment in time. I can tell you uniformly within this body what the temperature is. Right? Now, in reality, let's be clear. In reality, there is no such thing as a purely lumped capacitance problem. In order for heat to move at all, you have to have a temperature gradient. So if heat's coming in or out of this at all, there is going to be a temperature dependence on radius. For our purposes, if we want to just say, okay, about within 0.1 degrees, or we can estimate the heat loss or something like that, we don't really care if we get that little bit of accuracy. So first, to make this lumped capacitance justification, we're going to do the following. We're going to use our BO number. But the BO number is going to be a little bit different this time. So the BO number is going to be, conceptually, it's just resistance to internal conduction divided by resistance from the surface to the surroundings. All right, resistance to internal conduction divided by resistance from the surface to the surroundings. And what is that telling us? Right, that's telling us my temperature drop inside this sphere, the resistance to internal conduction, is hopefully really, really small relative to the temperature drop to the surroundings. That's all it's telling us. It's the same idea as the fin, like in the extended surface, right? We're trying to prove that in one direction there's no significant temperature difference. Same thing here. It's just we're expressing it for this transient problem. So, okay, I could rewrite that as my BO number is equal to our conduction internal divided by our surroundings. Our surroundings has to account for anything that is involved there. So if it's a contact resistance or convection or radiation or whatever, it has to account for all that stuff. But you will have to make that judgment as you're developing the problem. So for this particular problem, let's go through and compute what the BO number is. So what we're given, in this problem, we're given, let me just look back here. We're given, a heat transfer coefficient h bar. We're not told anything about radiation, I suppose. Let's neglect that to begin with. And so let's just say the resistance to the surroundings is R surroundings equals R convection, which is 1 over h bar times the surface area that's exposed, AS. Right, so then the resistance to conduction internal is going to be conceptually distance to conduct divided by conductivity times the area for conduction. All right, that's like the conduction conceptual definition. So I'm writing it this way because it's not entirely clear what my distance should be. I suppose you could make a case that the distance, the farthest that heat would possibly have to travel inside the sphere would be from 0 to the outer radius. That's true, but it's not necessarily reflective of the average distance that heat has to go, which is maybe more important for estimating the temperature drop. So there is a rule of thumb that you can use on transient problems to estimate the distance to conduct. And it is L conduction is approximately equal to the volume of the object divided by the surface area of the object. So this is kind of a way for any shaped body of estimating how far the heat kind of on average has to go. So if you go through this sphere example, you're going to end up with something that's, somewhere in like the 1/3 to 1/2 of the radius distance. Yeah, so okay, we can then go through and use this, rewriting what we have here. Oh, the area for conduction, right? So that's the denominator here. You can use the surface area AS if you want for that. Again, on average, it's going to be less than that. So this might be a not very conservative assumption, but it's usually a reasonable one. And I think, again, the point of this is not to get a high precision answer. The point of this is to show orders of magnitude. So if you go through this and you've made your surface area assumption and you end up with a BO number of 0.12 as opposed to 0.08, right? Does that really change your answer? Like, does it change your judgment about whether this is appropriate? Not really, because it's not really changing the ratios that much. So just, this is kind of a subjective thing. Keep that in mind. Okay, so area for conduction. Okay, so the surface of surroundings, we have our convection. And then what we would end up with is, let's see. Yeah, I mean, you can just take the ratio of these, which is the BO number is then length to conduct, which is volume over surface area. Let's see, and then it's conductivity in the denominator. Sorry, what am I doing? Let me erase this. So let's see, conductivity times our area for conduction, which is AS again. And then for convection, it is H bar times AS over 1. So one of those surface areas goes away. Right? So this becomes our BO number calculation. Hopefully I didn't mess that up. If we wanted to include radiation, you could do that, or you just have to put the radiation in the R surroundings term. So let's see. Let's actually quickly look at ease because I've done the calculation there. So what we want to do, again, is show the BO number. We want this BO number to be small. If it's small, we can say this is lump capacitance. So I've entered in all the information. I've actually also entered in information for the radiative resistance just to see if it's important or not. So remember, radiation is emissivity surface area sigma 4T bar cubed. I think, incidentally, in the homework solution for homework 2, I had T bar divided by 4. So I think I fixed that with the new version that was posted, but if you saw that, my apologies. All right, so we solve this problem. We end up with our BO number here. of much less than 1. So for this example, it is fair for us to model this as lump capacitance. You always want to go through this analysis. It seems unnecessary sometimes, but you want to do this just to see like how wrong you're going to be in the end. Okay. So
where did the T-bar come from?
Yeah, so T-bar that's a good point. So for this, what you'd say is, I actually don't know what the temperature of the sphere is going to be, but I do know it's going to be somewhere between ambient temperature and my, say the maximum that's shown on that plot of or initial temperature. Sorry, let me go back here and show you. We know the temperature of the surface here is going to be somewhere between initial temperature and maximum temperature. So if I wanted to get like a conservative estimate of the radiation resistance, I would want to probably pick a value that is somewhere like maybe closer to ambient. For the purposes here, what you're trying to do is find the lowest possible resistance to the surroundings. Because if you do that and you still prove that the ratio for the BO number is small, then that's like kind of covering your bases, right? So in that case, what you actually want is the highest estimate of radiation. So I might say, okay, I'm going to say T bar is actually like close to my maximum temperature that I know it would occur. Later on, you can go back and solve for T bar directly. But for the estimate, you might want to say, okay, I'm going to use 450 or 500 or something. If it's still small, then I'm good. And in fact, if we look at the solution there, we'd see that the radiation resistance here is pretty large compared to the convective resistance here, which means the amount of heat going through by radiation is relatively small, which I could ignore it. And even if I go back here and say this is T bar, where is that? There it is, 400. Even if I said this was 500, which is above my temperature, radiation is still small or large compared to convection, so it doesn't matter. Okay. I'd love to go further, but I don't think I have time. So let's leave it there. What we've done is justify that the lump capacitance is valid. What we'll do next time is talk about a lump capacitance time constant, which characterizes the time response of the system. So, okay, thanks everybody.